Welcome to the Nocturnal Astronomer. This is a place to slow down, let your thoughts drift, and lose yourself in the vast, quiet wonder of deep space. Whether you're winding down for the night, easing a restless mind, or simply looking for something beautiful to float away to, you're in exactly the right place. My name is Atlas Reed, and tonight I'm going to take you somewhere extraordinary. We're going to explore black holes. Not just what they are, but what they mean. The crushing gravity, the swallowed light, the way time itself bends and breaks around them. By the time we're done, I think you'll find that whatever has been weighing on your mind tonight feels a little smaller, a little quieter, a little more manageable. The universe has a way of doing that. Let's dive in. Fact 1. The black hole at the center of our galaxy is called the gentle giant. When most people hear the words black hole, they picture something like a drain in space, a dark circle pulling everything toward it, hungry and relentless. That image is not entirely wrong, but it misses something important. A black hole is not a hole at all. It is an object, one of the most massive and dense objects the universe has ever produced. At the heart of every black hole is a point called the singularity. This is a place where our understanding of physics quietly breaks down and stops working. The equations that describe the rest of the universe, the ones that have been tested and confirmed 1,000 times over, simply cannot describe what happens at the singularity. We reach it, and the math gives us infinity, which is another way of saying we don't yet know. Surrounding the singularity is the event horizon. This is the boundary, the point of no return. Anything that crosses the event horizon, light included, cannot escape. Not because something is pulling it back, but because space itself, inside that boundary, is flowing inward faster than anything can travel outward. The event horizon is not a wall, it is a threshold. From a distance, a black hole looks like nothing. That is not a poetic statement, it is literal. Because no light escapes, there is nothing to see. What we detect instead are the effects. Stars orbiting something invisible, gas heating to millions of degrees as it spirals inward, ripples in space itself, spreading outward like waves on a pond after a stone has been dropped. The first image of a black hole was captured in 2019. It showed a glowing ring of heated gas surrounding a dark center, the shadow of the event horizon itself. The black hole at the center of that image sits in a galaxy called Messier 87, which is roughly 55 million light-years from Earth. The image took a planet-sized telescope to produce. It took 8 observatories around the world working together to see something that no single instrument could see alone. That black hole contains a mass equivalent to 6.5 billion suns. 6.5 billion. If you tried to count to 6.5 billion, one number per second, it would take over 200 years. The thing we photographed is not just large. It is large in a way the human mind was never designed to process. And yet, here we are, processing it, quietly, in the dark. Black holes come in a few different sizes. Stellar black holes form when massive stars collapse at the end of their lives. They typically contain between a few and a few dozen solar masses. Supermassive black holes, like the one in Messier 87, contain millions or billions of solar masses and are found at the centers of most large galaxies, including our own. Our own galaxy, the Milky Way, has a supermassive black hole at its center. It is called the Gentle Giant by some astronomers, which is perhaps the most reassuring nickname ever given to something of such extraordinary size. It contains roughly 4 million solar masses. It is approximately 26,000 light years from Earth. It is not going anywhere, and neither are we. There is something calming about that, if you let it be. The black hole at the center of our galaxy has been there for billions of years. It was there before the dinosaurs. It was there before the Earth had oceans. It will be there long after every star in the sky has gone cold. Against that kind of permanence, tonight feels very small and very manageable. Fact 2. A clock at the event horizon would nearly stop ticking. Gravity is the force most of us understand least well, even though we feel it every single moment of our lives. We know it pulls things down. We know it keeps the moon in orbit. But the way gravity actually works, at the deepest level we understand, is far stranger and more beautiful than most people realize. Albert Einstein described gravity not as a force that reaches across space, but as a curvature of space itself. Massive objects bend the fabric of space around them, the way a heavy ball placed on a stretched sheet of rubber creates a depression. Other objects nearby roll toward that depression, not because something is pulling them, but because the shape of the space they're moving through has changed. Black holes take this to an extreme that no other object in the universe can match. The curvature of space around a black hole is so severe, so absolute, that it closes in on itself completely. This is why light cannot escape. Light travels in straight lines, but near a black hole, a straight line curves back inward. The geometry of the space itself forbids escape. This means that the closer you get to a black hole, the more dramatically time itself changes. This is not a metaphor. This is measurable, documented physics. Clocks run slower in stronger gravitational fields. A clock placed near the event horizon of a black hole would tick almost imperceptibly slowly compared to a clock far away in open space. Time, from the outside, would appear to nearly stop. If you could hover just outside the event horizon of a large black hole and somehow survive the radiation and tidal forces and look back at the universe behind you, you would see all of cosmic history playing out in fast forward. Stars being born and dying, galaxies evolving, billions of years compressed into moments. The universe would age around you while you remained almost still in time. This is not science fiction. It is a direct consequence of the equations Einstein wrote in 1915. Equations that have since been confirmed over and over again by experiments and observations. The universe genuinely bends time. Black holes bend it most of all. There is something quietly liberating about this. The idea that time is not fixed, that it flows differently depending on where you are and how strong the gravity is around you. The pressure we feel from time, the relentless forward march of it, the sense that there is never enough of it, is, in a cosmic sense, a very local phenomenon. Zoom out far enough and time becomes elastic, strange, something almost like a dream. The tidal forces near a black hole are equally astonishing. Gravity weakens with distance, and near a black hole, that change in strength across a short distance becomes enormous. If you fell toward a stellar black hole, feet first, the gravity pulling on your feet would be dramatically stronger than the gravity pulling on your head. The difference would be enough to stretch you in the delightfully grim term physicists use, like spaghetti. But here is something that surprises most people. If a black hole were massive enough, if its event horizon were large enough, the tidal forces at the horizon itself would be gentle. You could cross the event horizon of a supermassive black hole without feeling anything unusual at all. You would have no sensation of crossing a boundary. You would simply find, at some later moment, that you could no longer send a signal back. The point of no return is invisible, unfelt, passed in silence. There is something about that image that works well as a metaphor for sleep. The moment you stop being awake and start being asleep is also invisible, unfelt, passed in silence. You don't experience the crossing. You simply find yourself on the other side. Fact 3. A massive star's core collapses in less than 1 second. Every black hole tells a story that begins with a star. Not every star, but the largest ones. The ones so massive they burn through their fuel faster than anything else. Bright and brief and spectacular. These are the stars that end not with a whisper, but with one of the most powerful explosions the universe knows how to make. A star is, at its core, a balancing act. The gravity of all that mass wants to collapse inward. The energy produced by nuclear fusion pushes outward. For millions or billions of years, these two forces hold each other in check. The star sits in equilibrium, burning steadily, producing light and heat that travel outward across the cosmos. But fuel runs out. Every fire does. When a massive star exhausts the fuel at its core, the outward pressure disappears, and gravity, which has been waiting patiently for billions of years, wins. The core collapses in less than a second. Less than a second. A structure the size of Earth's orbit compressed down to something the size of a city in a fraction of the time it takes to blink. The collapse releases an extraordinary amount of energy, and the outer layers of the star are blasted outward in a supernova, one of the brightest events in the universe. A supernova can outshine an entire galaxy for a brief period. All the light of hundreds of billions of stars overwhelmed by the death of one. What is left behind depends on the mass of the original star. For stars of moderate size, a neutron star forms. A dense, spinning remnant the size of a city, but containing more mass than the Sun. For the very largest stars, the collapse does not stop at a neutron star. Gravity is too strong. The core continues collapsing until it passes through the event horizon, and a black hole is born. This process takes place across the galaxy, constantly. Stars have been forming and dying for billions of years, seeding the cosmos with black holes. The Milky Way alone is estimated to contain hundreds of millions of stellar black holes. They are not rare, exotic things. They are everywhere, quiet and invisible, scattered through the galaxy like seeds. The supernova that creates a black hole also scatters the outer layers of the star into space. Those layers contain elements forged in the star's core: carbon, oxygen, iron, nitrogen. These elements drift through space, eventually gathering into clouds, then into new stars and new planets. The atoms in your body were forged in the cores of stars and scattered by their deaths. You are, in the most literal sense possible, made of stardust. The iron in your blood was forged in dying stars. The calcium in your bones, the oxygen you are breathing right now, all of it passed through the interior of a star before it became part of you. The universe did not just produce you, it built you patiently over billions of years from the inside out. Black holes, then, are not just endings. They are part of a cycle, Stars live, die, scatter their matter across the cosmos, and that matter becomes new stars, new planets, new life. The black hole is what remains of the most dramatic part of that cycle, a monument to something that burned brighter than anything else, and then collapsed into silence. There is a kind of peace in that, if you are willing to find it. Everything that ends leaves something behind. Everything that collapses contributes to what comes next. Fact 4. Light can orbit a black hole without falling in. Light is the fastest thing in the universe. Nothing we have ever observed travels faster. In a single second, light covers nearly 300,000 kilometers. That is enough to travel around the Earth more than 7 times. It is enough to travel from the Earth to the Moon in just over a second. And yet, near a black hole, even light cannot outrun what it is falling into. The event horizon gets its name from an analogy with the horizon we see on Earth. Stand on a beach and look out to sea. There is a line beyond which you cannot see. Ships disappear past it, not because they have vanished, but because the geometry of the Earth curves away from you. The event horizon of a black hole works similarly. It is the line beyond which no information can travel back to you. What makes this so profound is that light is affected by it. Light, which has no mass, which travels at the ultimate speed the universe permits, is still trapped. This tells us something remarkable. The event horizon is not about being fast enough. It is about the geometry of space. Even something traveling at the speed of light through curved space can end up moving inward. Physicists describe this with a concept called light cones. At any point in space, you can imagine a cone pointing forward in time, showing all the directions a beam of light could travel. Outside a black hole, this cone points in all directions, more or less equally. But as you approach the event horizon, the cone begins to tilt inward. At the horizon itself, even the forward edge of the cone, the fastest possible direction of travel, points straight into the black hole. Once you cross the horizon, all possible futures lead inward. Not just the likely ones, all of them. There is no choice, no escape route, no direction that does not eventually lead to the singularity. This is what makes a black hole genuinely inescapable. Not the strength of the pull, but the structure of time and space inside it. Outside the event horizon, something interesting happens to light traveling near a black hole. Light bends around it. The gravity curves space, and light follows those curves, even when it is not heading straight in. This means a black hole acts as a lens, bending and distorting the appearance of everything behind it. Astronomers use this effect to study things that would otherwise be too distant to see. The most extreme version of this is a photon sphere, a region around a black hole where light can actually orbit. A photon travelling at exactly the right angle and distance will circle the black hole endlessly, trapped in a perpetual orbit. This shell of orbiting light sits just outside the event horizon, a ring of captured brightness going nowhere. Captured brightness going nowhere. There is something almost poetic about that. Light, which travels endlessly in straight lines across the cosmos, finally finding a place where it simply circles, not going in, not escaping, just orbiting, patient and luminous in the dark. If you were standing nearby, below the photon sphere, but above the event horizon, you could, in theory, see the back of your own head. Light leaving your head would curve around the black hole and return to your eyes. The universe reflected back on itself, your own existence visible from behind. Even the most distant reaches of the universe behave strangely near a black hole. Light from galaxies billions of light years away bends around it, creating arcs and rings and multiple images of the same distant source. The black hole makes the universe look at itself from angles that would otherwise be impossible. It is a cosmic mirror, warped and strange and endlessly fascinating. Fact 5. From outside, you would appear frozen forever at the edge. Of all the strange things black holes do to the universe around them, what they do to time is perhaps the most disorienting and the most useful if you are lying awake at night, worrying about things that feel urgent and overwhelming. Because time near a black hole is revealed to be far more flexible than our daily experience of it suggests. We have already touched on gravitational time dilation, the way time runs slower in stronger gravitational fields. This is not a small effect near a black hole. It is enormous. As you approach the event horizon, time from the perspective of someone watching you from a distance slows to an almost total stop. From their point of view, you would appear to freeze just above the horizon, growing dimmer and redder as the light escaping from you becomes more and more stretched. You would never quite disappear. The light carrying your image would keep arriving at the distant observer's eyes, but stretched thinner and thinner, slowing but never quite stopping. In theory, the last light you emitted before crossing the horizon would take infinite time to arrive. You would be, from the outside, frozen forever at the edge. From your own perspective, however, you would notice nothing unusual as you crossed the horizon. No alarm would sound, no sudden change. You would simply be falling, and then you would have crossed the boundary, and the universe behind you would have changed in a way you cannot undo. Time for you would continue normally. It is only the comparison between your time and the time of those far away that reveals the strangeness. This is one of the things Einstein's theory of relativity tells us most insistently. There is no single universal clock ticking away somewhere that everyone experiences equally. Time is local. It flows at different rates in different places, depending on gravity and velocity. Our intuition that there is one shared present moment, one now, is a local illusion produced by the fact that the gravity differences in our daily lives are too small to notice. A clock on the surface of the Earth runs slightly slower than a clock in orbit. Slightly. A fraction of a microsecond per day. But it is enough that the satellites providing navigation signals have to be corrected for it. If they weren't, the systems that tell you where you are would drift by kilometers per day. General relativity is not just a theory. It is baked into the technology you use to find your way home. Near a black hole, those effects are amplified to extremes that feel almost mythological. A traveler spending a short time close to the event horizon before retreating might return to find that thousands of years have passed in the wider universe. Their friends, their civilization, the stars they knew, all gone, aged into history while they floated in the warped time of a black hole's gravity. There is a way of thinking about this that is strangely comforting. The urgency we feel about time, the sense that it is running out, that there is never enough, is a feature of our particular place in the universe. Zoom out far enough, and time becomes something else entirely. Not a tyrant, not a resource being consumed, something stranger and more patient. The universe has been around for nearly 14 billion years. It will likely exist for trillions more. In that context, a sleepless night is not even a rounding error. It is less than a rounding error. It is an event of such extraordinary brevity that no instrument the universe has ever produced could detect it. That is not meant to make you feel small. It is meant to make tonight feel lighter. The universe is not in a hurry. The stars are not watching the clock. The black hole at the center of the galaxy has been there for billions of years, doing exactly what it does, slowly and patiently and without anxiety. You can borrow a little of that patience right now if you want to. Fact 6. A black hole's surface may encode everything that ever fell into it. One of the strangest debates in physics over the past several decades concerns a deceptively simple question. When something falls into a black hole, what happens to the information it contained? The question sounds philosophical, but it has kept some of the most brilliant minds in physics in productive disagreement for decades. Information, in the physics sense, refers to the precise state of every particle making up an object. Its position, its momentum, its quantum state. The laws of physics, as we understand them, say that information is never truly destroyed. It may become scrambled beyond any practical hope of recovery, but the information exists somewhere, in principle. But a black hole seems to destroy information completely. Anything that falls past the event horizon is gone. And when a black hole eventually evaporates through a process we will return to shortly, what is radiated away seems to carry no trace of what fell in. The information appears to have been erased. This is called the black hole information paradox, and it remains one of the deepest unsolved problems in physics. Stephen Hawking, who spent much of his career thinking about black holes, originally argued that information was indeed destroyed. He later changed his mind and agreed that it must somehow be preserved, though the mechanism remains unclear. There are proposals involving the idea that information is encoded on the surface of the event horizon, like a two-dimensional projection of everything that has ever fallen in. This idea, called the holographic principle, suggests something extraordinary. That the information describing the three-dimensional interior of a black hole can be fully encoded on its two-dimensional surface. And some physicists believe this principle extends beyond black holes, that our entire three-dimensional universe might, in some deep mathematical sense, be a holographic projection of information encoded on a two-dimensional surface at its boundary. If that is true, then the solid, three-dimensional world you experience every moment of your life is, at some level of description, a kind of projection, a hologram. The feeling of a pillow under your head, the weight of the blanket, the darkness of a room at night, all of it somehow encoded and projected from a surface you will never see and never touch. This is not a settled question. It may not be settled in our lifetimes, but the fact that it is a serious scientific proposal, considered and debated by serious physicists, says something remarkable about the universe. It is far stranger at its foundations than it appears from the inside. The things that fall into black holes leave their mark in ways we are only beginning to understand. A black hole's mass, its rotation, its electric charge, these are all influenced by everything that has ever fallen in. In that sense, a black hole is a record, a slow accumulation of everything the universe has contributed to it over billions of years. Nothing is truly lost. It is stored in a form we cannot yet read, encoded in ways we cannot yet decode, held in an object that will itself outlast almost everything else in the cosmos. The information is there. We just don't know how to find it yet. There is something quietly reassuring about that. The universe does not forget. It keeps everything, even the things that fall into the darkest places. Fact 7. Black holes take longer to evaporate than the universe has existed. In 1974, Stephen Hawking made a discovery that changed physics forever. He showed, mathematically, that black holes are not truly black. They emit a faint radiation produced by quantum effects at the event horizon. This radiation is now called Hawking radiation, and its implications are enormous. Quantum mechanics tells us that empty space is not truly empty. At the smallest scales, pairs of particles constantly pop into existence from pure energy, exist for a moment, and then annihilate each other again, returning their borrowed energy to the vacuum. This happens everywhere in the universe, all the time, invisibly and without consequence. But at the event horizon of a black hole, something different can happen. A pair of particles appears, one on each side of the horizon. The one outside the horizon escapes into space. The one inside falls toward the singularity. Because the particle that escaped carries away real energy, the black hole must provide that energy. And it does, by losing a tiny amount of mass. The black hole shrinks, imperceptibly slowly, but it shrinks. This process is called evaporation. Over an almost incomprehensibly long period of time, a black hole will radiate away all of its mass and eventually disappear in a final burst of energy. The timeline for this is staggering. A black hole with the mass of the Sun would take longer to evaporate than the current age of the universe by a factor so large it has more digits than there are atoms in the observable universe. Supermassive black holes would take even longer. We are talking about timescales that dwarf not just human history, but the entire history of stars. By the time the last black holes evaporate, every star in the universe will have long since burned out. Galaxies will have dissolved. The universe will be cold and dark and nearly empty, populated by nothing but slowly evaporating black holes and the faint radiation they produce. And then, finally, they too will be gone. The universe will reach a state of maximum entropy, maximum disorder, and begin what physicists call the dark era, an endless expanse of cooling radiation and the occasional random quantum fluctuation scattered through an unimaginably vast and empty space. This is the furthest horizon of time we can currently imagine. Against that backdrop, everything feels different. The drama of human history, the rise and fall of civilizations, the achievements and losses of individual lives, all of it takes place in a window so brief, it barely registers against the full timeline of the cosmos. We exist in a warm, bright, extraordinarily brief moment between the formation of stars and the slow evaporation of the last black holes. We are living in the interesting part right now. This unremarkable night, this ordinary moment of lying quietly in the dark, is happening during the rarest and most eventful period the universe will ever know. Stars are burning, galaxies are colliding, life exists. That will not always be true. On the largest timescales, it is almost never true. Hawking radiation is too faint to detect with any instrument we currently have. The radiation from a stellar black hole is so cold it makes the cold of deep space look warm by comparison. We know it exists because the mathematics demands it. We trust the mathematics because it has never let us down. And so we know that even the darkest, densest, most inescapable things in the universe are slowly, patiently, inevitably giving themselves back to the cosmos. Everything opens eventually. Everything returns. Fact 8. A quasar can outshine its entire galaxy by a factor of 1,000. The universe is not short of black holes. They exist at every scale, from stellar remnants a few times the mass of the Sun, to colossal engines billions of times more massive, sitting at the hearts of galaxies. They are not exceptions or rarities. They are among the most common massive objects the cosmos produces. In the early universe, just a few 100 million years after the Big Bang, the first stars formed. These early stars were enormous by modern standards, hundreds of times the mass of our Sun, because they formed from pure hydrogen and helium, with none of the heavier elements that help regulate star formation today. They burned fast, bright, and brief, and when they died, many of them left behind black holes. Some of those black holes grew quickly, consuming gas and merging with others, and became the seeds of the supermassive black holes we see at the centers of galaxies today. The black hole at the center of our galaxy, quiet and relatively calm now, was once perhaps an active, energetic thing, consuming enormous quantities of matter and radiating brilliantly across the cosmos. When a supermassive black hole is actively consuming matter, it becomes what astronomers call a quasar. The material falling in heats to extreme temperatures and produces an outpouring of energy that can outshine the entire galaxy surrounding it by a factor of 1,000 or more. Quasars are among the most luminous objects in the universe, and many of the brightest ones we observe are so far away that we are seeing them as they existed billions of years ago. Looking at a distant quasar is looking into the past, The light reaching us left its source before the Earth existed, before the Sun existed. We are observing a state of the early universe, a time when galaxies were younger and wilder and black holes were hungrier. The universe has calmed somewhat since then. The peak of quasar activity was roughly 10 billion years ago. We are living in the quieter, later years. Galaxies and their central black holes grow together, influencing each other in ways we are still working to understand. The mass of a central black hole is tightly correlated with the size of the surrounding galaxy, a relationship that holds across an enormous range of scales. This suggests they are not independent. They shaped each other over billions of years through gravity and radiation and the movement of gas. Smaller galaxies sometimes have what are called intermediate mass black holes at their centers, thousands of times more massive than a star, but millions of times less massive than the giants in large galaxies. These are harder to find and study, sitting in a size range we have less observational evidence for, but they are almost certainly there. And scattered through the space between stars are the stellar black holes, the remnants of collapsed massive stars. They float silently through the galaxy, invisible unless they happen to have a companion star to pull material from, or unless they pass close enough to something else to reveal themselves through their gravity. Most of them we will never detect. They are simply out there, in the dark between the stars, patient and still. The sheer number of them is astonishing. Hundreds of millions in the Milky Way alone, billions across the observable universe. Black holes are not the exception. They are a fundamental feature of what the universe does with mass when it has nowhere else to put it. Fact 9. One merger released more energy than all the stars in the universe combined. One of the most remarkable discoveries of the past decade is that we can now hear black holes. Not with ears, but with instruments sensitive to something called gravitational waves, ripples in the fabric of space itself, produced when massive objects accelerate. In particular, when two black holes spiral toward each other and merge. When two black holes orbit each other, they radiate energy in the form of gravitational waves. This causes them to spiral slowly inward, closer and closer, until they finally collide and merge into a single, larger black hole. The merger produces a burst of gravitational waves so powerful it can be detected across billions of light years by instruments sensitive enough to measure a change in distance 1,000 times smaller than a single proton. The first direct detection of gravitational waves came in September of 2015. Two stellar black holes, each around 30 solar masses, merged roughly 1.5 billion light years away. The the signal lasted less than a second. The burst of gravitational energy released in that fraction of a second was greater than all the light produced by all the stars in the observable universe combined in that same fraction of a second. One fraction of 1 second. More energy than all the stars in the universe produce in that time, released as ripples in space, spreading outward at the speed of light, washing through every galaxy they pass, gently stretching and squeezing everything in their path by an amount far too small to feel, but just barely large enough to measure. The gravitational wave passed through the Earth on that September morning in 2015. It passed through you, if you were alive then. It stretched and squeezed you by an amount smaller than an atom. You felt nothing. The universe shrugged, and something the size of a fraction of an atom changed in you, and then it was over, and you went on with your day without knowing. Since that first detection, dozens of mergers have been recorded. Black holes of various masses at various distances, spiraling together and becoming one. Each detection is a postcard from the deep past, a signal that left its source millions or billions of years ago and has been traveling through the universe ever since, waiting to arrive. The signal from a black hole merger carries information about the masses involved, the distance, the spin of the black holes before they merged. We can read the postcard, decode what happened, understand something that occurred before humans existed, before our sun existed, before our galaxy had taken its current shape. The universe speaks in gravitational waves, and we have only just learned to listen. Future observatories, some planned for space, will be sensitive enough to detect the gravitational wave background. A constant low hum produced by all the black hole mergers happening throughout the observable universe at any given time. When we can hear that hum, we will be hearing the universe breathing, the deep, slow respiration of cosmic structure, measured in mergers and ripples, and the long, slow spiraling together of impossibly massive things. That hum is already there. It has always been there. We simply did not have ears for it yet. Fact 10. The light from the nearest black hole has been traveling for over 1,000 years. We come now to the part that perhaps matters most, not for physics, but for the quiet minds lying awake in the dark tonight. Because black holes, for all their scientific strangeness, teach us something deeply human. They put us in our place in the best possible way. The nearest black hole to Earth that we currently know of sits about 1,000 light-years away. 1 light-year is roughly 9.5 trillion kilometers, 1,000 of those. The black hole sits in a system called the unicorn, a poetic name for something so extreme, and it is relatively small as black holes go, around 3 times the mass of our Sun. It is also, in astronomical terms, practically next door. And yet, 1,000 light-years is a distance so enormous that the light we see from that system tonight left before the Norman conquest of England, before the first universities were built in Europe, before Genghis Khan, before the Crusades, before the printing press, before almost everything we think of as modern history. That light has been travelling for over 1,000 years to reach us tonight, and that is the closest one. The supermassive black hole at the centre of our galaxy is 26,000 light-years away. The one we photographed in Messier 87 is 55 million light-years away. The most distant quasars we observe are billions of light-years away, their light carrying information about a universe so young it barely resembles the one we live in. Every time we look at the night sky, we are looking across distances and into a past so deep it humbles every sense of scale we think we have. Our planet is a small rock orbiting a medium-sized star in the outer regions of an unremarkable galaxy containing hundreds of billions of other stars. That galaxy is one of at least 2 trillion galaxies in the observable universe. 2 trillion, each containing hundreds of billions of stars, each star potentially surrounded by planets, and at the center of most large galaxies, a black hole containing the mass of millions or billions of suns. The human brain was not designed to hold those numbers. It was designed to track predators, remember faces, plan for next season's food. The cosmic scale is entirely outside its native operating range, and yet here we are, lying in the dark, somehow holding a fraction of it in our minds, a fact that is itself remarkable. Whatever is worrying you tonight, it exists in a particular life, in a particular body, on a particular planet, in a particular moment that will pass. It is real, it matters, and it is also, from the perspective of the universe, a single note in an incomprehensibly vast symphony that has been playing for nearly 14 billion years. That is not meant to dismiss what you're feeling. It is meant to offer it some company. The universe is large enough to hold your worry and 100 billion galaxies at the same time. There is room. You are not taking up too much space. You are not burdening anything. You are a small, warm, briefly luminous thing in a very large and mostly cold cosmos, and the cosmos does not mind you being here. Black holes are perhaps the universe's most powerful reminder of scale. They contain the mass of millions of suns. They bend time. They swallow light. They produce ripples that wash through the entire universe. And from where you are lying right now, you cannot see them, cannot feel them, cannot detect them at all. They are out there, doing what they have always done, patiently and silently. And you are here, breathing slowly, letting the thoughts quiet, letting the scale of things work on you gently, the way it always does when you give it enough room. The universe is large, the night is long, and you are exactly where you are supposed to be. And on that note, we bring this journey to a close. Tonight, we traveled to the edge of everything light can reach, traced the gravity that bends time itself, and sat with the strange, patient darkness of the most extraordinary objects the universe has ever made. Black holes are not just scientific curiosities. They are invitations to let go of scale, to remember that the universe is older and larger and stranger than any single worry has any right to be. I hope something in tonight's journey made the world feel a little quieter, a little lighter. I hope the numbers, the distances, the bending of time worked on you the way a deep breath works, slowly, without force, just making a little more room. Thank you for joining me tonight on the Nocturnal Astronomer. This is Atlas Reed, wishing you a peaceful rest. Until next time.